Yeah.
Yeah, makes sense. Very nice. Great, we got Federico.
Hello everyone, I'm Federico, and today I'm going to present the paper Behavior Planning of Autonomous Cars with Social Perception, so similar to the one that we just saw before. So when we speak about autonomous cars, we need to take in consideration perception and prediction. Those are the two key words. Perception is the ability of the car to perceive through sensors and cameras potential dangers that surround the environment, while prediction is the ability of act accordingly to our goals, like avoiding an obstacle or following a certain trajectory based on the perceived signals, inputs that we have. Of course, there are a lot of problems, such as uncertainties, errors, and occlusions, meaning that our sensors cannot understand everything that is going on in the surrounding environment. Well, but what if we don't want to rely only on our sensors and we want to understand informations also based on the behavior of the other cars and other humans around us? For example, look at this picture. We are in the red car, and there is like a human crossing the street, but we cannot see that. It's impossible for us to see that because there are two cars. What if we see that those cars are slowing down or braking? We can understand that there might be like a danger, okay, and act accordingly to that input that we receive from another human. Perfect. This is a control and the dynamical system problem, as like we just saw, and we have to take into consideration different states. For example, the states which means the speed, the position, acceleration of our car, of the other cars, and the states of the environment. Okay, so the road, is there an intersection, is there a red light or green light, or otherwise a signal that is giving us information. And the whole concept of the paper is to introduce a social information set I, which contains the information of the behavior of the other agents around us, such as are the people going slow, are they driving aggressively or not. And of course, this is a minimization problem. We want to minimize the control function and find an optimal, which will be given by the state vector UU of both human and our car, which are the control actions. Basically, in controls, once we receive the input through the sensors and other things, we can give an output based on the state that we just observed. And agent preferences, such as it's like a vector of the weights of the system. Like, we do want to be more safe, we want to do this. Again, like the problem is that we want to use other human drivers as external distributed sensors around the system to update our belief of the environment and the social information. We're going to consider two estimates, because this is we need to build an estimation models, and we can consider the state estimate of the car, meaning how does this is directly related to the probability, of a controlled output based on the state, which means how does the human action reveal the hidden state of the world? What if a car in front of me brakes instantly? There might be a danger. Okay, so I need to act accordingly. And the social information, same reasoning. So what social information, explains the behavior of other agents, like what does the behavior, a maneuver, or a speed of another human tells me about what is going on in the surrounding. And those are directly proportional both to the cost function that we want to minimize, and depending on the high value or low value of this cost function, there might be the probability is enhanced or not. To evaluate the problems, how do we do that? We do through an inverse reinforcement learning algorithm, because I need to learn the cost function of the human. If I don't know what the humans are doing, I cannot know what I will do next. And How does the inverse reinforcement learning algorithm work? It works basically creating a data set, UD, okay, which is like a simulation data set, with the goal of finding the weights, which are expressed by theta, okay, that will maximize the likelihood of the demonstration set. What does it mean? It means that I do not know like the human weights, so I do not know how the humans, like if the humans turn left or right, I don't know why the human does it. So I need to learn, okay, a certain action of the human with what a certain action of the human corresponds to. And to do that, I run the simulation, and I will find theta star, which is like the optimal weights vector, that will show me like which demonstrating trajectory have low cost, which means that have a higher chance of appearing. What does it mean? It means that through the algorithm we are not trying to predict the trajectory of the human, but we are trying to predict a weight vector that is gonna tell us which are the most likely trajectories that the human is gonna do in a way that we can act accordingly to these. And this is all the algorithm, and we can test it in a simulation environment which is based on the picture that we see here. We can imagine to be in the red car, okay, and there is an intersection with a human going inside the intersection crossing. And our view is, of course, blocked by the yellow car. So we need to rely on what the yellow car does. We can test our proposed algorithm here on the right, while on the left there is like an aggressive planner, so a standard algorithm which acts very aggressively. Okay, and the aggressive algorithm doesn't care about the behavior of the other human, so basically it doesn't see the human, and there is a chance that it will crash. Okay, while our algorithm sees that the other car is slowing down, so the inferred probability, so basically the probability that something might happen even if we don't see that, instantly spikes up, okay, so it reveals, okay, that there is a danger even before our sensors are able to capture it. And we can slow down the speed, and we can avoid the crash with the human in our way. Another scenario where we can test our algorithm to see if it works. Let's imagine the same environment as before, but this time there is no human. Okay, so the street is safe, there are no dangers, and we can test a conservative planner, meaning an algorithm that will act very conservative, very robust. And this algorithm, of course, takes unnecessary actions, okay, such as seeing the intersection and slowing down. So we have a loss in efficiency, because it's not efficient. While our algorithm, based on the behavior of the other car, that is gonna go straight because there are no humans crossing, there is no danger, is gonna, have a probability of 0 all the way down, not slowing down and gaining in efficiency, because relying on the behavior of the other car is able to understand that there are no dangers along the way. So this is the proposed framework, and what can we understand from this? We can understand that the result seems to be successful, meaning that our algorithm is able to understand, okay, based on the behavior of the other agents, understanding the state behavior, okay, of the surrounding of the other humans taking actions, is able to understand information that the sensors are not able to capture, okay. And so it seems to be very promising. But which are the complications that I thought, reasoning about this? First of all, we are considering a very simple scenario, right? So we're considering like one car and one human. So it's a scenario that it doesn't, in the majority of the cases, correspond to the reality. What if we are in a highway? What if you are in an environment full of obstacles, tens of cars, tens of humans doing different actions? Is it going to perform the same? Second thing, like we saw in the slide before, that here doesn't have some sort of robustness, so it's going straight on without like only relying on the other car. So how can we add additional robustness? Let's say that there is an error in some stuff that is going on the street. How can we add robustness, maybe to not as conservative as the robust algorithm, but being on a certain level of safety? And last, I is the most important, is like we are relying, we have our faith in our other car. So if the other driver makes a mistake or doesn't see, like we are gonna crash with him. So and this is like connected to the point that I just said before. So how do we avoid to have 100% faith on the other people? So that being said, thank you, and I'm ready for questions.
Perfect timing.
So in the crosswalk scenario, do you think this algorithm, or at least as they presented it, would break down if, let's say, the orange car sees the person and they slow down, but then they start to like speed back up because they know the person will cross their field of view, or they'll cross their path.
Yeah, so you're saying that the distance is like slows down and after accelerate because the human is already crossed
But the
yes.
human still occluded to the red car, and so then you start.
Yes, but at that point we will be able to see that the orange car slows down, so we're gonna be able to slow, okay, because we capture that there is a danger, and after there will arrive at a point where our sensors, I think hopefully will be able to see the human and understand that there is like a chance of hitting the human and slow down. This is true only if there is a degree, okay, where our sensor is able to detect the human, okay. So if the orange car is, like, will cover our, it's impossible because it will arrive at a point where we will have to see the human. So the question is, will we be able to achieve a velocity that will allow us to brake before hitting that? So I think yes, but I think it is connected to my point of add a certain degree of robustness to the algorithm to be fairly conservative without losing efficiency. I don't know.
Yeah, I was just wondering how
Yeah.
you think we handle this.
I was a bit confused on the two probabilities that you're trying to infer. So I understand that one is the state of the environment, the
Yeah.
transactions, but what is the social?
Yeah,
Why do
so
you need
the
that?
social information is the state estimate, okay? We understand that basically the action, okay? What is the, let's say we have a driver next to us, okay? And the driver is suddenly doing a maneuver, okay? What does the maneuver, okay, tells us about the state of the world? Meaning, if it slows down, there might be a red light, okay? So we have to stop. The social information is the old concept of the social perception, meaning that through the probability, we are estimating the probability, okay, that a certain action that the other human takes is related with the behavior of the systems that our sensors are not able to capture, okay? So it's different from the state estimate. This is telling us, if we are in a highway, okay, and all the people are driving aggressively, very fast, there are no dangers, okay? While if we see that the agent next to us is suddenly slowing down, the behavior indicates, okay, something that the state cannot make us understand, okay? Because through the state we understand only the dynamic, but through this social information we are trying to understand the reason why there is a change in behavior of the other agent.
More like
Yeah, yeah.
All right, thank you.